over the last few years, I've done like almost all of my program pretty exclusively in C. And despite that, I really haven't used malloc and free almost at all. And in fact, in most cases, I would really recommend using arena allocators, or at least other allocators composed on top of arena allocators. And that's for a few reasons that I'm going to get into. But let me just start off by showing you a quick implementation of like the most basic arena allocator you could have. So I've got a basic setup here of a C file just with some helper things. So I've made these type defs just because I prefer that syntax for typing. And I'm actually going to add in type defs for booleans. Right click that. And then here we got some macros that'll give you like kibibytes, megabytes, gigabytes, which is going to be useful later when we're talking about initializing arenas, and then min-max, whatever. Okay. Anyways, what is an arena allocator? Sometimes it's called a bump allocator, sometimes it's called a linear allocator, but really all it is, and I'm going to start making our struct here, is it just a block of memory that you like linearly allocate. So you have a pointer to some large block of memory, and then every time you allocate, you just return wherever you are right now, and then add whatever size it was, right? It's as simple as you can get. Like, you can't free from the middle, you can go like linearly from the top and bottom. It's just a stack. So for our most basic implementation here, we're going to have a 64 capacity, right? And then we're also going to have a current position, and you'll see how we actually get the position of the buffer in a second. So now I'm going to make just a little interface here. So we're going to have mem arena, we're going to have an arena create function that takes in a capacity. We're going to have a corresponding arena destroy function. And I just prefix it with mem because usually arena is like the variable name. If you feel free to use whatever kind of convention you want for that. So now we're going to do the function to allocate memory is going to be called arena push. Remember, we're dealing with a stack here, so we're going to be pushing memory to the arena of some size. And then we're going to also have a function that lets us pop from the end of the arena like that. So it'll pop there, and then we can also we can just make some simple pop2 that'll pop to a specific location, right? And then we can also do arena clear, which will just clear all the memory in the arena, just like that. So this is our little interface here, and then what I'm going to do here. So obviously in real life you would have separate files for this, like arena.h, arena.c, whatever. But for this example, I'm just going to put everything in the one C file here. So let's start off by implementing these. Okay, so come down here, and then what we're going to need, I'm actually going to make two constants here. The first one is going to be the base position. So instead of actually having a pointer in the actual arena structure that points to the data, I'm just going to take the pointer to the arena itself as the start of the buffer. I don't know if that makes sense right now, but when we implement the arena push function, hopefully that'll be clear. But the arena base pos is just going to be the size of memory, right? Because the first thing that we're going to allocate with this big block of memory is the arena itself. And then the other thing I'm going to find here is an align. So for various reasons, computers are much better at dealing with memory that is aligned to its kind of like word size. On modern 64-bit systems, that's likely going to be 8 bytes. I'm just doing whatever the size of a void pointer is because that'll give us like the size at which the computer works, right? If it's a 32-bit machine, that'll be 4 bytes, most likely. Anyways, so for this, like I said, for this most basic version, I am just going to be using malloc for this, but you'll see in a bit we're going to modify our arena to make it a little more powerful. So our arena, and then our capacity is the capacity here. Our position is arena base pos, like that, right? And then our destroy function, we're simply going to free the arena. Okay, so now moving on to the pop. Remember, for popping to the arena, push. Why do I keep saying pop? For pushing to the arena, all we're going to need to do is return the pointer to its current position, and then increment the position to the next position, right? So, but again, remember we have that whole alignment thing to deal with. So I'm going to take the position and then use my helper macro here to align it up to a power of 2, and that power of 2 is going to be arena align. And then what we're going to do is say new position equals the align position plus some size, right? And if the new pause is greater than our capacity, then we fail to allocate. Feel free to deal with this error however you want. In my actual arenas, I generally just flat out crash the program. Like, I assume that if you can't allocate memory, it's already too far gone. But you do you. And then we're going to take our output pointer, which again is going to be the current position, so at pause align, not a new pause. Actually, the first thing we need to do is actually update our position to be the new position. Can't forget that. And then what we're going to do is, like I said, we're treating the arena itself as, or the arena itself, the pointer to the arena. Oh my god. Like I said, the pointer to the arena itself is the start of our chunk of memory. So I'm just going to grab that pointer here directly, convert it to a U8 pointer. That way that if we do pointer arithmetic with it, it's going to be in bytes aligned, right? If you don't know how pointer arithmetic works, don't worry about it. Just know that the U8 makes it work. And then we're going to do plus pause aligned, and then just return out like that. Oh, one more thing that I do generally like to do here, hopefully, can you still see that? Okay. Is I'm going to add another argument here that says non-zero. And what this is going to do, by default, I generally like to zero out memory. Because especially if you're going to be pushing and popping to it a lot, that can help get rid of some issues. And generally computers are fast enough that it is zeroing memory is not going to slow you down to any significant effect. So just do that right there. And then for arena pop, all we're going to do is we have to make sure the size is not too much, and then we're just going to remove size from the position. All right, so all I'm going to do here is say size equals min of size, and then whatever the maximum size that we can pop, right? So that's going to be the arena position minus arena base pause, right? And then just subtract size like so. And then pop 2. Because we're dealing with unsigned integers, we need to make sure, well, in pop 2, all I'm going to do is call pop, right? But we need to make sure, because we're dealing with unsigned integers, that we don't wrap anything, or underflow, overflow, yeah, underflow. So our size is going to be basically arena, the current position minus the pause that we want to pop to. So we need to check to make sure that our position is less than our arena's position. If it is less than that, then we're going to go arena pause minus pause. Else we're going to do arena, if it's not, we're just 0, right? If it's greater than the arena pause, there's nothing to pop, right? And then pop and arena size like that. And then we're going to do for arena clear, all that is and then for arena clear, all we have to do is pop to our base position. Like so. All right, so that is literally it. So one of the primary reasons I like arenas so much is just how dead simple they are, right? Our allocations and deallocations here are stupidly fast, right? Like all we're doing to allocate is adding a number basically and returning the whole thing and the mem set. All we're doing to pop is subtract a number. It's so ridiculously fast. And the other thing that one of the primary advantages of arenas that I love is that you end up having an asymmetric allocation strategy. Now, if you want to really dive into why arenas are good, I would recommend reading this article by Ryan Fleury, kind of I don't know if the person who popularized arenas, but he really brought arenas to my attention at least. And one of the things he talks about is that with malloc and free, like we're doing here, it has to be symmetrical. For every single malloc, you have to free, right? If you're mallocing like 100,000 small things, you have to individually free each and every single one of them, right? When you're dealing with arenas here, everything that you push onto the arena gets like freed automatically when the arena gets destroyed or cleared or whatever, right? So you end up with this asymmetric style where you can do a bunch of small allocations and then deallocate them all at once. And that's one of the reasons that it's really powerful. So yeah, we got that interface done. And then one thing that I do like to do, and you can kind of put this wherever. Actually, I'm going to put this below here, is to create some helpful macros that'll let you push and pop or push to the arena given some type. So if I'm going to define push struct here, and that'll just take arena and type, and then will automatically cast arena push, and then I'm gonna call, so we're gonna get arena and then just size of type, right? Should probably, just for good practice, and then not 0, and then we're gonna add another version that does non-zero. So again, the basic one here, this one will 0 the memory, and then the one here will leave the memory empty. And then I'm going to add 2 more here that do arrays. So this will also take an integer n, and then we're simply going to do size times n. Now, do not forget the parentheses here. I've made that mistake before. One of the reasons that macros can be a little bit iffy, but in this case, remembering the parentheses, you're going to be fine. So yeah, we have an arena. We can do mem arena. Usually I create a permanent arena in my main function, and then this is just going to be equal to arena create, right? And then we can destroy the arena, and I just realized I typed out capacity, which makes no sense. We'll give it a megabyte. And there you go, you're off to the races. If you want to create some foo pointer, you just say push struct foo, right? And that's it, right? So that is it for the basic arena. That's literally it. I mean, what do we have here? Like 50 lines of code? Not even, right? But I'm going to show you a trick that makes arenas way more powerful, and it's really not too much extra work. But to explain that, I first need to talk about virtual memory for a second. So back in the day, computers, if you had a pointer, that would literally point to an actual physical address in your RAM, right? But nowadays, it doesn't actually do that. Pointers in your program, right? Like this pointer, the perm arena right here, is a pointer to what's called virtual address space, right? Instead of being like a literal position in your RAM, it's a position in virtual address space. And then your computer has what's called the memory management unit, which can map from virtual address space to actual address space. And for a number of reasons, this makes computers both more secure and more flexible. You avoid memory fragmentation. But the cool thing about virtual address space is that because it's not actual memory, you can reserve a section of virtual address space. So to your program, it looks like you just have an insane amount of contiguous data, right? But to the actual operating system, to the actual computer, you're not using that memory until you tell the operating system you want to, right? So we're going to modify Arena here to use virtual address space and show you how to do it on Windows, right? So what we're doing here is actually slightly platform specific. So I'm going to show you the Windows version, and then in the code I'll link in the description, I'll have a Linux version, or kind of a Unix version. I don't think it works on Mac, although maybe that was just my compiler flags. But anywho, what I'm going to do, so we're going to need four functions for our interface here. I'm going to prefix them with plat for platform. We're going to have a reserve function, right? And this is simply going to take a size. That will reserve size bytes in virtual address space. And then I'm going to have this one return a Boolean indicating whether or not it is successful. And all this is going to do is commit that portion of virtual address space. And then we're going to do decommit. Take another pointer, another size. And then we're going to do final mem release, which will take, if I can type, void pointer and size. So this is our interface, and like I said, I'm going to show you the implementation for Windows. Although one more thing that I will add here is a function to fetch the page size from the operating system. Now this isn't entirely necessary, but virtual address space, all these operations have to be done in increments of your system's page size. Likely it's going to be 4 kilobytes or 4096 bytes, but just to be safe, I do add that function there. So now I'm going to do if def win32, and then put our functions here. So page size is pretty simple. It's a function called get system info. I need to include Windows first. So all we got to do is create system info, and then get system info, and then just return sysinfo. I think it's DW page size. Perfect. And then here are the virtual memory interface on Windows is virtual alloc and virtual free, right? So it takes an address, for this is going to be null, a size, and then like a action to do, so reserve, and then this one takes a access specifier or something. This one also takes the permissions, right? So this is part of why virtual address space allows a little bit more security, because the pages that we're going to be committing here are going to be able to read and write from them, but we won't be able to execute them. If you're dealing with something more complicated like a JIT or something, you might want to be able to execute from pages, but generally it is much safer to not have that for now. And then to commit, it's going to be the same thing. We're going to do this and then say mem commit, and then same access, and then successful when the return value does not equal null, right? And then for this one, we're just going to say virtual free, and I did not spell that right. Virtual free, which will just take our access or size, and then how much, like to what capacity we want to free, and size, and then mem release, and that's pretty much it. Like, these are some just standard wrappers of all these functions, right? Okay, so now we need to modify our arena struct to actually use our new interface. So instead of a capacity and a position, we're going to have some reserve size, and then we're going to be committing blocks of data in some commit size, right? So I'm going to have a reserve size. This is analogous to our capacity. Commit size, this is like the chunk size for our commits. And then we're going to have a position, and then we're going to have a commit position, right? What did I just do? So this is where the actual memory is. This is where the committed memory is, right? So, and then we're also going to need to modify, so create will take in a reserve size and a commit size, like so. Okay, so now, in our create function, well, first let me update the arguments here. We're going to get rid of most of this. So, first thing I'm going to do is get our page size using the function we made earlier, like so. And then what I'm going to do is round up our reserve size and our commit size to be aligned to page boundaries, right? If you recall from earlier, I said that all of these virtual memory operations have to be done in blocks of pages, right? So this is just going to ensure, given any arbitrary reserve size and commit size, that we are actually doing that properly. And then what we're going to do is attempt to, first thing we need to do is actually reserve our thing. So we're going to say plat mem reserve, and that's going to be our reserve size. And then what we're going to do is attempt to commit the first commit in memory, right? Now, technically you could run into a situation where your arena size and your arena size is bigger than a page and your commit size is small enough that you couldn't actually fit in it, but like almost certainly your actual memory in a struct is not going to be 4 kibibytes, because I don't know what more information you would need. So we're going to commit arena commit size, and if that fails, again, I'm just going to return null. But in my real applications, I would just fail here, because if you can't commit this page, you're kind of screwed. And then let me fill in these things here. So our reserve size is reserve size, commit size is commit size, and our position is arena base pos. Our commit pos is also our commit size, right? Because we've committed that much memory, right? And then this one, we're simply gonna, for the destroy function, we're gonna place free with mem release and arena reserve size. All right. Now for the push function, this is where it gets exciting. So for most pushes, we're going to be pushing into committed memory. So there's really not much more to do. Again, even with this fancier stuff, arenas are still crazy fast. Okay. So this check right here is going to be reserve size if we've reached the capacity. And then the other thing I'm going to do here is check if our new position is greater than our commit position, right? And now what we need to do is calculate where our new commit position should be and then commit the memory up until then. So I'm just going to start off by saying our new commit pos is just directly our new pos. And then I'm going to align it up to our commit boundary. So I'm going to add to it the commit size -1. And then we're going to subtract from it the new commit pos modulo the commit size. Like so, that'll align it up. And then also just going to make sure that it does not go above the reserve size. Right? That's our new commit pos. And then what we need to do is first get the pointer to the current commit, or the end of the current commit, and then the size of the commit. So for that pointer, we're going to say, just call it memory or whatever, and that's going to be the arena plus the current commit pos, and then our commit size is going to be our new commit pos minus our arena commit pos. And then again, here we go, we're going to say plat mem commit at our memory of commit size. And if that fails, I'm just going to return null. If that succeeds, we need to update our commit pos to our new commit pos, like so. And that should do it. Now, for this implementation, I'm actually just going to leave the pop here. Now, you might say, well, aren't you still, if you commit a bunch of memory and then pop a bunch of memory, don't you still have that memory committed? And you'd be right. I do, in some of my implementations, I will decommit memory, or I'll even have an optional flag in the arena that lets you control whether or not you want your arena to decommit memory. But in a lot of cases, you're going to be like reusing around the same size of memory multiple times when you clear an arena. So you might as well just leave that memory committed, right? Up to you. But you could easily figure out how to modify it. So now, our arena create function has two arguments, actually. We have a reserve size and a commit size, right? And the specific numbers here don't matter all too much. You really have a lot of virtual address space to play around with it. So, I mean, a gigabyte is probably a little excessive. There's probably an amount of memory where your application would stop working anyways. I would just pick something relatively reasonable. And what you can also do, I'm not going to do this in this video because it would get far, far too long, but you can actually make chains, like a whole linked list of arenas, where if you exceed your reserve size, you create a new arena entirely, add that to the linked list, and start committing from that arena. If you want a good example for an implementation of that, I would look at Rad Debugger's arena. It was what I used to base my arena code off of initially. Now that we have this done, allow me to demonstrate the power of this style of arena using virtual memory, right? So if I arena push, right, onto the perm arena, and I'll do, say, like 16 megabytes, right? And then I'm just going to throw it in a get C here so we don't use up all my memory. Then, here, let me compile this. And I just have the default, so it's a.exe. So now, look at this. a.exe right here, the first one in the background processes. And now I'm going to type enter, so watch this. I reserved a gigabyte of memory, right? But a gigabyte is not being used by the application. Only 48 megs is right now. And if I keep typing enter, get additional 16 more, right? So you only pay for the memory that you need, basically, is how it works, right? And this is really, really powerful. But honestly, this is just scratching the surface for arenas. I still haven't gone into chaining arenas, like I said, scratch arenas, all that. So let me know if you want me to make another video about arenas, but I hope that some of this convinced you or showed you how powerfully these arenas can be, or at least how fast they can be. Come on, that's all that really matters, right?